Welcome to lecture 3 of this particular course, which is statistical thermodynamics. So in this particular course, we are going to look at this particular lecture will cover as a continuation of the previous lecture, which is basically on probability and statistics. So now let's take a look that we covered the different permutation combinations and stuff like that. Today we are going to look at binomial distribution first. Okay, so binomial distribution. So it is any sequence of experiments or trials with two possible outcomes. Example are, say for example, tossing of a coin. So this has got two possible outcomes. Here the outcome is head or tail. So there is only two possible outcomes. Now, say that the coin is biased. So normally head or tail should have equally likely when you toss a coin. Now say that the coin is biased. Okay, so let us assume that probability of obtaining a head is, say, P. P is the probability of obtaining a head. Therefore, since there are only two possible outcomes, therefore probability of obtaining a tail is 1 minus the probability of obtaining a head, and let's call it Q. So you understand, because the sum total of these two probabilities should be 1. So it could be either a head or a tail. So this is the premise. Now let us assume now for a sequence of n tosses, say n tosses. So you toss the coin n number of times. Okay, the probability of m heads, okay, and therefore n minus m tails in a particular sequence. Sequence is p to the power of m, q to the power of n minus m. As each toss, why this is possible? That is because each toss, as we can see, each toss is an independent event. In a new sample space, correct? So that is the probability that for a sequence of n tosses, probability of m heads and n minus m tails in a particular sequence is given by p to the power of m multiplied by q to the power of n minus m, as each toss is an independent event in a new sample space. Okay. However, now a little bit of twist. However, m heads and n minus m tails can be obtained in more than one way. Okay, it can be obtained in more than one way. So what is that? It is like is like number of ways, okay, in total objects, okay, can be arranged, okay, in m identical objects of one kind, okay, and n minus m identical objects of another kind. So therefore, the probability of tossing m heads and n minus m tails is given by Bm, okay, given by n factorial divided by m factorial n minus m factorial, right, and e to the power of m 1 minus p to the power of n minus m. So this should be clear. This we already learned from our previous lecture, right? So it is like how n total number of objects can be arranged in m identical objects of one kind and n minus m identical objects of another kind. So therefore the probability becomes this multiplied by that. Okay? So this is nothing but, if you look at this, okay, this is nothing but C n comma n, which is basically the combination that we covered in the last class, right? So it's a combination. So this, once again, is the well-known binomial probability distribution. N is the total number of repeated trials with only two possible outcomes. Okay. All right. So that is what it is, and the mean of such a distribution, which is written as n bar, is given as np, and the standard deviation is given as np into 1 minus p, which is also written as npq. Okay, so this is the mean and the standard deviation, okay, of binomial distribution. Is the mean and the standard deviation of binomial distribution. Okay, so this is already something that we know. I mean, we may have read it earlier. Okay, so let's look at now the next possible distribution, which is called a Poisson distribution. So what is a Poisson distribution? It's like a binomial distribution. Okay, so you take a binomial distribution, only in this case n is very large. That means it approaches infinity, and a very large number of trials, and p goes to 0. That means the probability of m is very low in each trial. So you can think of it as a very biased coin in which, the heads and the tails are not half, but the probability of getting a head is very low. Okay. So in this case, if you write the binomial distribution, you will have, if you just open up things a little bit, right, is n minus n plus 1, okay, divided by n factorial. So this entire thing is then multiplied by, write it in red, it's given by mu n to the power of n and 1 minus p raised to the power of n minus n. Okay, where your mu is equal to your m bar, this is equal to np. So this is basically the mean. Okay. So in the limit, the binomial distribution where n approaches infinity, this becomes n raised to the power of n divided by n factorial, mu by n raised to the power of m into 1 minus e raised to the power of n. Okay, so if we revise it further, okay, n approaches infinity, dm is given as mu n into n factorial into 1 minus e raised to the power of mu by t. Okay, in the limit p goes to 0, 1 minus e raised to the power of 1 by t given as e to the power of minus 1, where e is basically, as we know, 2.71828 roughly. Okay, so in the combined limit, where basically n goes to infinity, p goes to 0, okay, p raised to e of the Poisson distribution is e to the power of minus mu to the power of m divided by m factorial. Okay, so in the case of the Poisson distribution, the sigma is given as np, which is nothing but root over mu. Okay, so this is the Poisson distribution. So the Poisson distribution, if we just recap, it is when n is very large and p is very small. So what we have done is that we have taken the binomial distribution, applied the two limits, and we ultimately get this. Okay, where the standard deviation is given by this. So this is the Poisson's distribution. This is the Poisson distribution, which some of you may be familiar with also. Okay, now let's look at the next distribution, which is basically called the Gaussian distribution. So what is a Gaussian distribution? This time your n is large, but e is not small. So unlike the Poisson distribution, where p was also small, in this case e is not small. Okay, but n is still large. So what we have over here is, let's take the log, write it in smaller forms. Factorial plus okay, so this is just a log where q is 1 minus p. Then we apply what we call a Stirling approximation. Okay, so Stirling approximation states that logarithm of n factorial is n into ln n minus n plus half ln 2 pi n. Okay, so this is the Stirling's approximation. So we can show ln of the binomial distribution is given as, and this is a little long, given as ln 2 pi n to n minus n, first term. Let us call it term 1. Okay, then of course we have np by n raised to the power n. Let's call it term 2, and then plus ln nq n minus n minus n. This we call it, say, term 3. Alright. So these are the 3 terms. Now let us define y is equal to m minus m bar, which is basically m minus np. Therefore, m by n is equal to y by n plus p. Okay, and n minus n by n is equal to q minus y by n. So now we take term by term. Here we define 3 terms, remember? So we take now term by term, right? So let's take term 1. So let's take term 1. This is term 1. Okay, so in the limit n goes to infinity, mu by n minus m, okay, is given as a limit n goes to infinity. Okay, let's write it in the next line, y plus n plus p into q minus y by n. This is equal to n q. Okay. Okay. So see if you can understand the first term. That is what we did. The first term we got to that particular sequence. Okay. This is the first term. Now, as your y by n, okay, y by n scales with the relative width of the binomial distribution. Okay, we previously found to display this binomial distribution exhibits 1 over root n type of dependence. Okay. So for the remaining 2 terms, therefore, 2 terms, ln np by m raised to the power of m is equal to minus n ln m by np is further given as minus y plus np into ln 1 plus y by np. Okay. Now the other term, which is ln nq divided by n minus n minus n, that is given as minus n ln n minus n by nq, which is further given as minus nq minus y ln 1 minus y by nq. Okay. So for the employing the logarithmic series, employing logarithmic series, which basically tells you that ln of 1 plus minus z is almost equal to plus minus z minus z squared by 2 for all z less than or not z less than 1 at moderate values of p. Values of p, right? At moderate values of p. Okay, so in a nutshell, that translates to y squared np minus y, and in the limit, other limit, ln nq by n minus n is almost given as y minus half y squared by nq. Okay. So now, if you substitute all these terms, that means this term, right? So this term, and of course your NPQ term, which is basically this particular term, into the parent equation, of, that we already narrated, that is the binomial equation in the logarithmic form. Okay, we get, so substituting, we get the limit n goes to infinity ln dy is equal to minus half ln 2 pi npq minus y squared by 2n 1 by p plus 1 by q. Okay, so this now results in a Gaussian distribution, which is given as gy, which is nothing but root over 2 pi n pq exponential minus y squared 2n pq. Is a Gaussian distribution. And of course we know that sigma square is equal to npq. Okay, and define z as y over sigma. We obtain, employing these two, we obtain a more palatable form of the Gaussian distribution, which is 1 over 2 pi sigma exponential minus z squared by 2. Okay, so this is the Gaussian form that you may have encountered. Okay, so for a continuous distribution, the discrete variable n must be replaced by its continuous analog x. Okay, so that the Gaussian distribution, as we know, this is symmetrical about z because of its dependence on z squared. And unlike many of the cases for discrete binomial or Poisson distributions, this Gaussian distribution indicates that the peak value of g is always at 1 over 2 pi sigma. So this is always where the peak value of this g is always given by this. Okay. So the Gaussian distribution is shown to be a satisfactory approximation of the binomial distribution if your NP is greater than 5 and NQ is also greater than equal to 5. So the Gaussian distribution holds the probability for a specified range of variables, therefore is given as, say, if your x is between these two, is essentially integrating the Gaussian distribution from, over the two limits. Right. So that is what the Gaussian distribution is all about, and this is how we get the Gaussian statistics as well. Okay. So now that we are almost, so the Gaussian distribution, as you know, it is very symmetric. We already said that. Okay, so we started with the binomial distribution, and for the Poisson distribution, we saw that P was very small and N was large to get the Poisson distribution. Then if you go to Gaussian distribution, your N is large, but your P is still finite to begin with. Okay. So few other things, that for a Gaussian distribution, your Z is x minus mu by sigma. Mu is once again equal to NP. Okay. GZ, just write it down, is symmetrical about Z, as it is dependent on Z square. Okay. Peak value on GZ, again I'm writing this explicitly, is always at 1 over 2 pi sigma. Okay, so, and let's see what else we have got. So this is the most convenient method of calculating the probability, this particular method, when you actually have your probability follow a Gaussian distribution, which in many cases it does. It does follow the Gaussian distribution, and so you can actually this is the most useful way of calculating the Gaussian distribution. As we know, Poisson's distribution you may have already read in your undergraduate. That is also very useful. A few words, that all of these are valid when there are only two outcomes for a sequence of experiments. Any sequence of experiments, like tossing of a coin, like any other things which has got any two outcomes. It is widely used not just in stat thermo but in economics and a lot of other subjects as well. Okay, so and also where the Poisson distribution is applicable. It is applicable for a process which involves a photon counting. Photon counting means where the total number of photons are counted, because n is a very large number, but the possibility of observing a single photon is very low. So that is like P approaches 0. So that is one example of a Poisson distribution that you may be wondering that what it does, right? So similarly, there can be other types of distributions also, but we are not going to go into the details. In the next class, we are going to cover what we call the combinatorial analysis of statistical thermodynamics. So that is going to be the subject of the next class, which is going to where we are going to see some of the differences between distinguishable and indistinguishable objects, and then go on to the further statistics like Fermi-Dirac and Bose-Einstein statistics respectively. So thank you, and this is the end of lecture 3.